Hi, my name is Jenna Tran, and this is my Lab O5 presentation on the gravity of a falling object. In this presentation, I'll walk through the purpose of the lab, the methods I used, the physics behind it, and how the experimental results compare to the computational model. The goal of this lab was to investigate how closely the real motion of a dropped object matches the motion predicted by a computer simulation. To do this, I used a paper ball as my system and dropped it while recording its motion. For the experimental portion, I used Tracker, which allowed me to analyze the motion frame by frame. For the predicted motion, I used GlowScript to build a computational model based on physics equations. By comparing these two approaches, I was able to evaluate how accurate a theoretical model is when applied to real-world motion. Here are the physics principles of this lab. So this lab is based on the momentum principle and fundamental laws of physics. The key idea is that the net force acting on an object equals the rate of change of its momentum. In this case, the dominant force acting on the ball is gravity, which can be written as mass times gravitational acceleration. This means the object experiences a constant downward acceleration. Using these principles, I can update the velocity of the object and position over small time intervals. This step-by-step updating process is what allows the computational model to simulate motion over time. So for the actual procedure, it consisted of several main steps. First, I imported a video of the falling object into Tracker and marked the position of the ball in each frame. This produced a data table of time and vertical position values. Next, I used the initial conditions for Tracker, such as initial position and velocity, to build a computational model. This model generated its own set of predicted time and position values. After that, I entered both data sets into a spreadsheet and plotted them on the same graph. This allowed for a direct visual comparison between the experimental data and the simulation. Finally, I analyzed the similarities and differences between the two sets of results. So for the tracker data, you can see on the slide the interface along with the recorded data points. Each point represents the position of the ball at a specific moment in time. By marking the ball frame by frame, I was able to capture how its position changed as it fell. This data reflects the actual motion of the object and serves as the experimental baseline for comparison. From the tracker data, I calculated the initial conditions needed for the model. The initial position of the ball was approximately 1.38 meters above the ground. I also estimated the initial velocity by calculating the change in position over a small time interval. This value gave about a negative 0.909 meters per second, indicating that the ball was already moving downward slightly at the start of the measurement. These values are important because they directly influence how accurate the computational model will be. Using GlowScript, I created a computational model to simulate the ball's motion. The model uses a loop to repeatedly update velocity and position over small time steps. At each step, the net force, mainly gravity, is applied and the object's motion is recalculated. This method closely follows the momentum principle and allows the simulation to approximate continuous motion. In some cases, additional forces like drag can be included, but even a simple gravity-only model can produce results that closely match real motion. This slide compares the experimental data from Tracker with the predicted data from the model. Both graphs show a clear downward curve, which is expected from an object under constant acceleration due to gravity. The overall shapes of the graphs are very similar, indicating that the model is fairly accurate. However, there are small differences between the two lines. These differences become more noticeable over time and highlight the limitations of the model and the experiment. Overall, the experimental data closely followed the same trend as the computational model, showing that the model is a good representation of real motion. However, small discrepancies were present. One source of error may be inaccuracies in marking the center of mass in Tracker, which can slightly shift the data points. Additionally, the paper ball was not a perfect sphere, so drag forces may have acted unevenly on it. Air movements in the room could also have affected how quickly the ball fell. These real-world factors are not always perfectly accounted for in the simulation, which explains the differences between the two results. In conclusion, while the computational model is highly effective, experimental conditions introduce small variations that prevent a perfect match, but ultimately, it's good enough. Thank you.